So first initially connect the signal generator through this input, and the VCO output is connected and fed back to the VCO input. Now you observe the waveforms on DSO. So when the input signal frequency and the signal generator input frequency signal is in phase, the phase error is 0. We have to note down these frequencies, that is FC1. So initially when the signal generator frequency is increasing like this, so at one particular frequency the free running frequency and the input signal frequency is matched. This is nothing but capture range. So you can note it down, that is FC1 is the input signal frequency exactly the same phase of the system frequency, that is free running frequency F0, that is the phase error is 0. We have to note down these two frequencies here, that is FC1. So the input signal frequency of channel 1 is FC1, okay, that is 2.57. Now we slowly increase the function generator frequency. At one particular point, if you observe the waveforms here, so it slowly deviates. There is some phase error from the input signal to the VCO frequency, so that we can mark it as in the FC2, that is FC2, that is capture range. So once it is 180 degrees out of phase, so you can note down this frequency as a lock frequency, that is FL2. So this frequency goes on increasing, so that the signals, the two signals are out of phase, so that is lock range, that is we have to note it down FL2. So like that here, so initially first switch on the system, note down the free running frequency. You are not connecting any wires, so switch on the system and note down the VCO, that is free running frequency. Once you can connect the function generator through a cable through this red node, okay, so the VCO output is connected to the VCO input, and you observe this signal generator frequency is increasing. At one particular point, the two signals, the two waveforms are in phase, the phase error is 0. We have to mark it down the FC1. So once it is out of phase, what we say that it is the phase difference is 180 degrees, that frequency we can call it as a lock range, that is FL2. So for different frequencies you can note down the FC1, FL1, FC2, FL2. So like that here, from these two different ranges, so this is again the lock range, that is FC2. Again this is FC2. Again it is out of 180 degrees out of phase. This is FL2. So for at particular, the input signal frequency is increasing. At what particular point the two waveforms are in phase each other, that we have to note down FC1. When it is out of phase, you can note down FL1. So like that you can note down the readings. So that is the difference in capture range, that is lock frequency, and the difference in lock range, that is the lock range frequency. So always the difference of frequencies of FL1 and FL2 is lock frequency. The difference of frequencies, that is capture frequency, is a capture frequency. So this is the PLL experiment. So we estimated capture frequency, lock frequency, and the difference between the lock and capture frequencies. So always we have to note down these two frequencies and find out the lock range and capture range. So always we have to mention that capture range frequency is always in this range and the lock range is in this range. So always, so if you calculate this, FL is always greater than FC. Okay, so this is the way you have to estimate two different terms, that is lock range and capture range. And initially switch on the system, you observe the free running frequency. So these are the waveforms. So one is switch on the system, observe the system design F0 frequency. So once you can connect the input from the function through function generator, and the VCO output is connected and fed back to the VCO input, then observe when the frequency, the input signal frequency is increasing, we have to observe the lock range and capture range of two waveforms. Okay, so this is the way you have to estimate the lock range, capture range and free running frequency. So already in the observation book we have different calculations. By using the formulas we have to calculate it and draw the model graphs of the lock range and capture range. Okay, so this is the experiment. I hope it is clear about these different terminologies: capture, lock and free running frequency. Okay, so what is lock range means? The range of frequencies over which the PLL maintain the lock within the incoming signal is called lock range. So this is the lock range. The phase difference is maximum here, and the range of frequencies over which the PLL occurs lock with a input signal is called the capture range. So when the input signal frequency is increasing, at what certain frequency both the waveforms are locked each other, that is a capture range. So two values we have to FC1 and FC2, you have to note it down, and then 180 degrees phase shift of the two signals we have to note it down, FL1, FL2. Okay, so initially first draw the waveform of F0. So when the input signal is connecting to this circuit, then these two waveforms are 180 degrees each other, so you have to note down the FL1 lock range. Again these two signals are same phase, that is FC1. Again you change the input signal frequency at certain point, the input signal frequency and these F0 frequencies again out of range, that is FL2. So from these values we have to calculate the difference of lock ranges is FL, difference between the capture range is FC. So if you plot this, FL is always greater than FC. So this is the way you have to do the experiment. So you observe the waveforms. So simply you can change the input signal frequency at what certain frequency the two waveforms are locked each other, and otherwise there is a phase difference between the two, that we can call it as lock. So once it is captured, the phase difference is 0. Okay, so this is the way we have to estimate the different parameters in phase lock loop experiment. Okay, thank you.